Ladies and gentlemen, please welcome George Saab.
Hi, good morning. Welcome to Java 1. I'm very pleased to be here to introduce our next speaker. And I wanted to say, one of the things that I think a lot of us have in common is we're completely sure that what we're doing is, it's very complex. It's very advanced, right? Is there anyone who doesn't do advanced stuff in the audience? I know my team that makes the JDK and the JVM, we know that what we do is rocket science. Well, the next guest is actually somebody who really does rocket science. Our guest has a master's and PhD from USC, and she was the lead systems engineer for the revolutionary, what's it called? The revolutionary parachute, which was used in the landing of the Mars Curiosity rover. She also is the project manager now for the Cold Atom Laboratory at JPL. She's come to visit us from Southern California, but we're not going to hold that against her. Please give a warm welcome to Dr. Anita Sengupta.
Thank you for the intro, George. Well, thank you for having me, everyone. I'm going to go get my clicker. As I'm the presentation, I'm going to go through some interesting slides for you. So my background is aerospace engineering, which is also known as rocket science. So everything that I've done for several years has been related to either speeding things up with propulsion systems or slowing things down with retro rockets and with parachutes. And so the topic of my talk today is probably a bit of a departure from some of the other topics of this conference, but it is how do we explore Mars, and specifically how do we use engineering to get us to the red planet? And so several years ago, I had the opportunity to work on the Mars Science Laboratory mission, which landed the Curiosity rover, which you see here in this picture. So Curiosity is essentially a robotic geologist, and it's the largest robotic geologist that NASA has ever created and sent to the surface of Mars. And one of the largest engineering challenges of being able to send something the size of a small car to a planet which is 400 million kilometers away is to land it safely on the surface. And so I was part of the engineering team which developed that system, and it was very much a highlight of my career. And so for reference, what you see here in the background is the planet Mars. And so our job was to land the Curiosity rover, which departed Earth on a launch vehicle, into a crater called Gale Crater about 9 months after we initially launched it. So I'll talk a little bit about the engineering challenges associated with how you design that type of entry, descent, and landing system, and then talk about exactly what the rover has been doing on the surface and why it's so fascinating for us. So first of all, how do we land on Mars? We created a wonderful video called 7 Minutes of Terror, which was intended to sort of engage the planet Earth and children and adults alike as to the challenges of landing something on a planet so many millions of miles away. And it takes you 7 minutes to get from the top of the atmosphere down to the surface of the planet. So please enjoy.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought. But it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun, 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
A parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we gotta cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just gonna smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms, and it could damage instruments. So the way we solve that problem is by using the sky crane method.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage away to a safe distance from the rover.
So what's so exciting, of course, is that appears to be science fiction, but in fact it's science fact. So we were able to engineer that very complex system and safely land the Curiosity rover on the surface of the planet just over 4 years ago today. So first of all, though, people like to ask me, why is it that we're so interested in Mars? And this drawing that you see here shows you a photograph of the Earth taken from space and a photograph of Mars taken from space. And you can see that the planets are quite different from each other. But at the beginning of time, when the solar system first formed, we actually believed that Mars did have an atmosphere, a thick atmosphere, and it had appreciable water flowing on the surface. So something happened over the course of the past several billion years, which made Mars evolve into a dry, dusty, cold rock compared to Earth, which obviously has very large oceans and a thick atmosphere with oxygen so that we're able to survive on the surface. But what that means, though, is that if we were to one day go and colonize another planet in our solar system, would we want to go to Mars? And the answer is actually yes, because even though Mars doesn't have appreciable water on the surface, it probably still has it in the subsurface, which could be used by future human colonies. And the other benefit of Mars is it's not that far from Earth. It's a smaller planet, but it does have about 1/3 the gravity, so it's not as difficult to be able to survive in a 1/3 G environment as opposed to a 0 G environment. There is an atmosphere. We actually use that atmosphere to slow ourselves down during the entry, descent, and landing sequence that you just saw. And so you could conceivably use that atmosphere, which primarily contains carbon dioxide, to make fuel, such as methane, if you brought enough supplies with you. Now, it is a much colder planet than Earth because the atmosphere is very thin and it's further away from the sun. But if you can imagine, during the Martian summer day in the equatorial regions, it actually can get to a temperature on the order of California temperature. Although, of course, during the wintertime, it can get much colder at minus 120 degrees Fahrenheit. The big challenge, of course, though, is that the atmospheric pressure is quite low. It's only about 1% at the surface as of what it is on Earth, which means that if you were to live on the surface of Mars, you would have to bring your own air supplies with you, as well as live in a pressurized environment. But compared to the Moon and compared to the vacuum environment of space, Mars is actually far more habitable compared to what it would be if we were to go to a more distant planet, for example. The one challenge, which isn't too much of one, however, is that the Martian day is only slightly longer than the Earth day. So even our bodies wouldn't have that difficult of a challenge to be able to be accustomed to 24.6 hours versus 24 hours. But what is so fascinating about Mars, though, is that it's had an active geological history. So one of the reasons why we do space exploration is to understand how did our solar system evolve, how did our planets evolve. And what we do know is that in the past, Mars was actually very volcanically active. And what you see up here is Olympus Mons. Olympus Mons is the largest mountain in our solar system, and it's an extinct volcano. It's 3 times as high as Mount Everest, so that can give you the scale of how large this volcano was and the amount of material that it probably did spew across the surface millions or billions of years ago. But now the volcano appears to be inactive, and we don't understand why. Why did we have all this volcanism in the past, but don't appear to have it now? We actually are sending a mission very soon, which is going to look for evidence of Mars quakes if they are still present. Another really interesting feature is Valles Marineris, which is sort of the scar that goes across the center of the planet. And it's kind of akin to Mars's Grand Canyon. So at some point in Mars's past, there was a lot of water flowing on the surface. But where did the water go? Is it frozen in the subsurface? Did it all evaporate off of the atmosphere? And the way we answer some of those questions about why the volcanism changed, how did that change the environment of Mars, where is the water today, is by sending spacecraft to orbit Mars, as well as rovers and landers to explore the surface, to take scientific measurements for us. So Mars actually has moons. Not everyone is aware of this. They're called Phobos and Deimos. They're relatively small, which is the reason why they kind of still look like potato-type structures. They haven't crushed under their own gravitational force. And one potential architecture is to actually, for us to go and visit those moons, set up a telecommunications relay, and potentially mine valuable minerals or even water that might be on the surface of these moons as a future sort of human mission architecture. So by a show of hands, who thinks we found water on Mars? Well, we actually have. And so we have found water frozen in the subsurface region. What you see in this picture is a Phoenix lander, which was in the mid-2000s, came down, was landing on its retro rockets, kicking up all of the dust and soil. And the little patch that you see beneath it is actually frozen water ice. So it's like a salty water ice brine. So we know there is water. It's in the surface, and we would have to tap into it if we were in future to be able to send people there to utilize it from a colonization perspective. Now, a really new finding, I would say, which is in roughly the September of 2015 time period, is that we actually confirmed that we found flowing water on the surface of Mars. And the picture you see on the upper right, and all of these images are taken by a spacecraft called MRO, the Mars Reconnaissance Orbiter. And it takes beautiful, high-resolution images across the entire planet. And those black streaks that you see going across this image and coming down on this image are actually seeps of water from the subsurface material which comes down the sides of cliff faces. It's not that much, it's seasonal, but we do still see it, which means that we can potentially tap into these subsurface aquifers. And what might reside in that water, we don't know until we actually go and visit it. And so we have a lot of data as to what the surface of Mars looks like from both an engineering perspective, and then we're collecting more data to understand what it means from a scientific perspective. So we have landed on Mars a total of 7 times now with the US space program. We're the only space program to date which has been successful. Other ones have tried but haven't been successful. It's a very difficult thing to do, so we build off of our prior experiences. We had the Viking landers, which landed in the 1970s. You can imagine the computer technology that was available at that time, not so much as probably far less so than what you have even in your own individual smartphone. We also landed the Pathfinder rover, which was about the size of a Tonka truck. We landed that in the 1990s. In the early 2000s, we landed the Mars exploration rovers, which is roughly the size of a lawnmower. There was 2 of them, MER-A and MER-B. And then We had the Phoenix lander, which was in the mid-2000s, and then August of 2012 was the Curiosity rover. So each time we have these missions, we build upon our expertise from an engineering perspective from the prior missions, and we increase our scientific knowledge base as we go again and again to the surface to collect more information. And we have 2 missions which are coming up now, which is the InSight mission, launching in 2018, which is going to look for evidence of Mars quakes. And we also have the Mars 2020 mission, which is going to send another rover to the surface and cache a sample to hopefully bring back to Earth one day for further analysis. And these are all images that were taken of the rovers over time in these individual missions. So what I'd like to show you here is the evolution of technology. So ironically, in the evolution of computer technology, you start big and you go small. In the evolution of rover technology, we start small and go big. And the reason for that is that you can carry more scientific equipment if you have a larger platform. So if you were going to move your house, you wouldn't move it on the back of your bicycle, right? Or on the back of a motorcycle, you would move it on the back of a large moving truck. And so as we increase the wheelbase and increase the mass that we can send to the surface of Mars, we can make more interesting scientific measurements. And so you can see the evolution from the small Tonka truck-sized rover going all the way up to the Curiosity rover, which has also a new power system, which enables it to go to more interesting terrain over larger rocks and operate for a larger portion of the day. And I'll talk to you a little bit about what some of that scientific equipment is that it's carrying on its back. So the Mars Science Laboratory mission specifically was there to assess whether or not Mars could have once been habitable and could still be habitable today. And the way we do that is by making a series of scientific measurements. One of them is to look to see whether or not there could be any biological potential. And we do that by taking a look at are organics present? Are the building blocks of organic molecules present? We want to also understand how the rocks and the minerals formed. Did they form due to water-based geological processes or something else? And we also want to understand what the radiation environment is. So if any of you have seen The Martian, I assume most of you have probably seen The Martian, one of the biggest challenges for sending people to live on the surface of any other planet in our solar system or moon in our solar system is what is the radiation environment going to be like? And so this is the very first mission where we actually make measurements of what the surface radiation is, which will allow us to understand, do we need to develop new shielding technologies? And what kind of environment are we going to see if we live on the surface for extended periods of time? So that actually is a really big challenge that we have ahead of us. And so we do that by carrying a suite of scientific instruments on the back of the rover. So then, of course, the obvious question becomes, where are we going to land the rover, right? Mars is a large planet, just like Earth is a large planet. So we have to pick a location which is going to be scientifically interesting. So if you were an alien race coming down to Earth and you were looking for life, would you go to the middle of the Sahara Desert? Or would you go to the middle of the Amazon rainforest? You go to the rainforest, right? So on Mars, we don't have that exact same sort of geographical selection because the planet has lost most of its water. But there are regions on the planet which did have large water bodies, and so we selected a location called Gale Crater, which you can see on the lower image here, where we believe there was an ancient riverbed or lake bed present. And where better to look for evidence of past sedimentary rock formation or even past organic molecule deposits than the base of an ancient water body. So we selected Gale Crater, and then just for reference, for those of you who are fans of the Mars program, MSL, Curiosity rover, was landed in Gale Crater. The prior rovers, the Mars exploration rovers, were landed in Meridiani. So there are a very large distance between them. So unfortunately, you can't drive from one to the next because you're not able to drive out of the crater. And if you remember from the Martian movie, he was actually able to go over and pick up the RTG from another rover and use it for his power system. So we don't have the capacity to do that because we actually don't have the driving distance capacity, which is actually largely driven by computational constraints for our flight computers that we use, which is an interesting aside. So in terms of Gale Crater, this is what it looks like in a three-dimensional sense. And so for scale, this is